we're now going to summarize. So this is the part 2 of so this is part 2 for this narrow escape calculation. Alright, so we discussed in the first part the Green's function, and we said that the solution of Laplacian u equal -1 can be written in the integral form using this equation u epsilon. This is the Green's function, the integral of the Green's function. We have here the flux term. This is the flux on the absorbing boundary, and this is a constant which was the integral of u. And now we are going to use the condition that u of x equals 0 at the boundary, which means that we have this condition. So the flux by definition is unknown. We don't know what it is yet. And so now as epsilon goes to 0, really this term here is going to be of order 1. And the constant c, which depends on epsilon, we know that c epsilon will go to infinity, because c epsilon is, as we have seen before, this is the average of u epsilon. Let me go back just to show you the what it was. This is 1, 2. So let me change color. So this was, no, this is the order 1 term. This is u epsilon, and this is the average, right? And now we keep the flux. So let's go back now into the where we are. Okay, so how we need what? We need precisely to find the c epsilon and to find what is the flux. So to do this, we are going to use the conservation of the flux. So if we start from the equation Laplacian u equal -1, and we integrate everything on the volume, what do we get of everything? So we have the following: integration of Laplacian u by definition. So this is by the definition of the equation is -1, and -1 over the volume, it's minus the volume of omega. Now if we use the divergence, the Gaussian integral, this is just du dn ds, and now we can only restrict ourselves to the absorbing part, and this is equal to minus volume. So let me write it this way. And now this is quite interesting, because since the volume is small, and now we are going to make an assumption that du dn is a regular, which is not the case in dimension 3. But in dimension 2, we can make this approximation that du dn can be written making a Taylor expansion. Let's call it g at 0 at the center of the so we need here to define precisely what's the boundary. So this is the absorbing part, d omega a. And now let's suppose that this is 0, the origin. And so now we can let's say this is, by definition, if this is small, as this is epsilon divided by 2. And we can parameterize everything by the curvilinear axis. So this is j of 0, let's say at point S, plus S, j of 1. This is just a Taylor expansion, plus, etc. Alright, so what do we get? So the flux compatibility condition, which is du dn ds equals minus omega. Now this can be written as integration from minus epsilon divided by 2 to epsilon divided by 2 of j0 plus j1s plus etc. d. So this is ds equals minus omega. So the leading order term, this is not hard to find, that can be written this way. This is J0 is minus omega divided by epsilon. Now this is J0 is a constant. And of course, in general, it's more complicated. We have an equation, we have an expansion, but the leading order term is the following. Right, so this is important because now we will be able to use this in the flux condition. So let me write the condition for the flux. So we have J, there's a green function, PQ, du dn of P, dsP, this integration over d omega A. This was minus the constant C epsilon. So from the compatibility condition, we know the leading order term for the flux. So now we have to write everything using the expression for the flux. So if we take P, let's take the point P here to be 0. The origin, so this is a domain. We have here the absorbing part. This is 0, and this is epsilon divided by 2. So now P is the 0 point, so P0 and Q, we can always write it this way. This is minus 1 divided by pi log of S, this is the curving axis, plus, you know, some other one term that we are going to neglect in the first approximation. So we have here to discuss, or let me remind you that we don't have here, we have not 2 but minus 1 because this is due to the image charge. Okay, so I think we are ready now to calculate. Let's plug the Green's function and u. So we have to integrate from minus epsilon divided by 2 to epsilon divided by 2 of what? Of minus 1 divided by pi log of S, and then multiply by J0, which has to be equals to minus the constant C epsilon. Okay, so now let's finish the calculation. So by symmetry, this is integration from 0 to epsilon over 2. Now there is minus 2 divided by pi, and we have log of S ds multiplied by J0. And now the leading order term of this, so we integrate by part log of S, so this is just epsilon, this is S log of S, so we have epsilon divided by 2 log of epsilon divided by 2, so this is the leading order term, right? So this is in the leading order, multiplied by 2 divided by pi multiplied by J0. Alright, so let's continue. Finally, we have the constant minus C epsilon, which is going to be equals to, so we have J0. So J0 was, so let's write it J0, and we have epsilon log of epsilon divided by 2 divided by pi, right? And there was this minus, so J0 was minus omega divided by epsilon. So finally we have C epsilon equals omega divided by pi log of epsilon divided by 2 plus O of 1. This can always be written because 2 is really O of 1, so this is log of epsilon. And I think yeah, so this should be C epsilon. Let's go back to see what we get. C epsilon, yeah, so C epsilon has to be positive, so minus equal minus, yeah, so I think there was a minus here, right? If we go back, this is minus C epsilon in here equals this. All right, so finally we get that C epsilon, this is C epsilon, so there should be another minus equal minus this, so C epsilon should be 1 divided by this, and this is exactly the mean first passage time to the small hole. We just solve now the mean time it takes to reach the absorbing part. Now there is something that we have to finish for this calculation is the fact that what happened now if we go back to the equation for u of x, so this is C epsilon, but there was an integral of the Green's function plus there was this flux term, so this is over omega du dn j, let's say x and y, d sy of y, and this is d omega. So this is of order 1 term. Now this C epsilon, now if a point x does not belong to the boundary layer, and this is very important, the Green's function here becomes of order 1, right, with a fixed sign. So finally this, the entire term here, can be written as du dn, and this is order 1, multiplied by this d omega a, and by definition this is the integral of Laplacian u, which is minus omega, so which is bounded, right? So this is really the leading order term. Now if x is in the boundary layer, then what we just discussed is incorrect, and then the behavior of u of x actually depends on x at leading order. All right, so I think I wanted to show in these 2 classes this calculation. I think it's very informative and give ideas of how things have to be can be done using Green's function. So we are done now with this asymptotic expansion. The next class I will discuss the difference in dimension 3. We are going to use the Green's function, and the differences is that we are going to see that the flux is not anymore constant but has a shape. Actually it is given for when you have a disk of radius epsilon, it is given by epsilon squared minus r squared. And then we will see also the second order term. The second term has to do or uses the curvature, the mean curvature at the center P. Let's call it P. This is the mean curvature. We will do many holes. So how can we study using the Green's function the escape through either hole A or B? So this is going to be the next. We'll see that in the next class. And finally, we'll discuss the diastrate time, which is the time it takes to escape when you have a cusp. And for this, as we're going to see, we will use conformal mapping. is going to be a conformal mapping to precisely send this part here of the domain into something more regular. So this will be sent to a domain in R2. Right? Okay, so I'll see you for the next classes. Thank you very much.